Hi, I'm Scott Snyder. I'm going to generate a video that illustrates how to use SPSS to um, compute and analyze a repeated measures factorial design. In this case, the repeated measures will be on Peabody Picture Vocabulary Test scores, PPVT. PPVT is a measure of receptive vocabulary of individuals. This is kindergarten, first, second, and third grade. The RW stands for Rosh Wright scores, which are scale scores. So we expect these scores to increase across time because it's the nature of the scaling. Our analysis in this case will be to determine whether or not there is a relationship between the changes across time in the PPVT scores with the with the main effect of child sex and with family risk and with the interaction between child sex and family risk. That is, we're trying to see whether or not changes across time on receptive vocabulary vary as a function of the child's gender. We're going to see whether or not changes across time vary as a function of the level of psychosocial risk that exists within the family. And we're going to see to what extent the changes across time in receptive vocabulary vary as an interaction of family risk and child sex. So to do that, we're going to go to Analyze, General Linear Model, Repeated Measures. Our first factor, our within subjects factor, in this case is going to be grade or time. So I'm going to call it grade because we are going from kindergarten to first to second to third grade. That will be 4 levels. We'll put that in there. I'm going to now define what these 4 levels are. So click on Define. Gives us our data set. I have these 4 levels all contiguous to each other. So I'm going to block them and I'm just going to send them over. We need to make sure that they are in the correct order, first, second, third, and fourth, as we had anticipated. We are then going to look for our between subjects factor. One of them is child sex. The other one is family risk. This is just a filter variable that limits the family risk components to the first 5 levels, 0, 1, 2, 3, and 4. So I rejected anything that's above 5 because the sample sizes of those were too small. We're going to go over to Model and make sure that we have full factorial checked. It is type 3. We'll continue. We are interested in, since we have multiple time periods here, one of the things we probably need to look for is whether or not we have a polynomial effect associated with these grade levels. So this is going to let us know whether or not the effects of grade are linear, cubic, quadratic. So we're going to click that. We're going to get down. For child sex, there's only 2 levels, so we're not worried about it. For family risk, we might want a contrast, a simple contrast. So we click continue there. Go to plots. So grade is going to be on the horizontal axis. So in general, we always want, to the extent possible, we want either an ordinal or a repeated measures value along the horizontal axis because it will make looking at change more sensible. So we're going to send grade to the horizontal axis. We're going to run different plots here. So the first time we'll have separate lines for family risk and separate plots for child sex. Click Add. The next time, again, horizontal axis is going to be grade, but this time we're going to put family risk as separate lines, actually as separate plots, and child sex as separate lines. Click continue. Don't know what just happened there. Grade by child sex, separate plots for family risk. Click add, click continue. We're going to come down here to options, and we are going to click descriptives, effect size, homogeneity tests. A number of people click observed power, but frankly I know that we have 1,500 subjects in this case, so we're going to have plenty of power. Click continue, and we're going to click OK. Running it. Analysis has been completed. You see that we have a fairly equal distribution of levels of gender, and we have fairly kind of a normal-ish distribution of family risk. Most of our subjects are within level 2, but we have 30 that are at very low risk and 47 that are at significantly higher risk. We have our descriptive statistics that are provided for, so this is the kindergarten scores. You can take a look at these. I'm not going to take our time to go through and make an interpretation here. We're going to skip down to the box test. So this is a bit of a concern. So the homogeneity of variance test when we have repeated measures is done with the box test. This is also the test that we use when we have any other type of multivariate data. So we know that the box test is highly sensitive to variations. We have lots of subjects in this case, but this level of significance, so we have some people that argue that if as long as this value here is not less than 0.001, we can proceed. In this case, it is less than that. So we have reason to believe that we have a violation of homogeneity of variance and covariance matrices, which suggests that we have problems with the comparability of our cells across time because the variances are not equivalent. We're going to proceed for this illustration, but I want you to understand that first of all, box M is highly sensitive, but once we drop much below 0.001, we may be in an area where the consequences are somewhat concerning. We tend to assume that ANOVA designs are fairly robust to violations of homogeneity of variance and homogeneity of variance or covariance matrices, but we should exercise some caution in our interpretation here. So we're going to skip. We're not going to interpret this time as a multivariate test. We're going to skip down here to the Mauchly's test of sphericity. So sphericity is kind of like the assumption that that different combinations of time-dependent variables or repeated measures variables are share common variances. Another way of thinking about it would be that the correlations between time 1 and time 2, or between time 1 and time 3, and between time 2 and time 4 are all the same. And that's a very difficult assumption for us to meet. So we often run into a situation where that test of sphericity, so that's that particular test of homogeneity of variances or covariances across repeated measures, we often violate that. So in our case here, we're going to look at an adjustment to our degrees of freedom. It's going to be the greenhouse geyser adjustment. We're going to go down here then, and our focus is going to be on interpreting the greenhouse geyser. And what you see happening here is that we have the same type 3 sums of squares. So our total sums of squares are still the same. We're just using a slightly different degree of freedom, which gives us a population variance estimate that is a little bit different because instead of dividing that number by 3, we're now dividing it by about 2.5. So it gives us a larger population variance estimate than we would have had if we were able to assume sphericity. So as we are looking at this, the first test we have is the test of grade. So this is our time effect. This is our within subjects effect. And what we see is we reject the null hypothesis that PPVT scores are equivalent across time. This should not be a surprise to us because we were using Roche-Wright scores. So since we're using scale scores, we were expecting scores to change across time. So we have a significant effect there. That's not the surprise. The grade by child sex, so this is the question of whether or not the effect of time is equivalent for males and females. So the null hypothesis is that the effect of time is equivalent for males and females. We do not reject that interaction. We don't reject the null hypothesis for that interaction. These scores are greater than 0.05 or greater than 0.01, so we do not reject the assumption of parallelism between grade and child sex. The next one is family risk. So this is a question of whether or not the impact of time is the same for each level of family risk. We had those 5 levels of family risk. Again, we look across the greenhouse geyser. Whether we use an alpha of 0.05 or an alpha of 0.01, we do not reject the null hypothesis of no interaction. Okay, the null hypothesis here is that the effect of time is the same for all levels of family risk, which is typically described as the parallelism hypothesis. So in this case, we do not reject that those lines are parallel. We do not reject that there is no interaction. We see that the partial eta squares are very, very low, less than 1% for each one of those. And again, we wouldn't be as concerned about these partial eta squares since we don't reject the assumption, we don't reject the null hypotheses. The three-way interaction, the more levels of interaction that we get to, the more challenging they are to interpret. But it's just arguing that the effect of time does not vary with the interaction. Does not vary with the interaction of child sex and family risk level. These are contrasts. Again, this is telling us that there is a linear effect, a quadratic effect, and a cubic effect for grade. The cubic effect basically means that there's kind of 2 curves. Quadratic effect means that there's 1 curve. Linear effect means that it's just a straight line. We see that the greatest amount of partial eta square is explained by the linear effect, but the fact that we have a significant cubic effect suggests that this is a fairly complex curvilinear relationship that we are looking at as the effect of PPVT across these 4 grade levels. We look at the test of homogeneity of variance when we are looking at the individual analyses of these scores. The between subjects effect, so these are, if we're just looking at the effects of family risk or child sex, what we see is that across time, so when we average the PPVT scores across all 4 grades, there are differences due to level of family risk. Okay, so this is when we average across all 4 grade levels for PPVT, there is a difference in PPVT based on the level of family risk. There is no difference due to gender. Okay, so when we aggregate all of the PPVT scores across the 4 years and across all levels of family risk, there is no difference based on the gender of the child. And again, there is no interaction when we aggregate across all 4 years. There's no interaction between child sex and family risk. The impact of family risk is equivalent for each gender, and the effect of gender is equivalent for each level of family risk. Here is our evidence of parallelism. So for one sex, you can see that these lines, while they diverge a little bit when we get to 3rd grade, in general, there's a lot of parallelism, that the effects of grade level are pretty consistent across the different levels of family risk. There's parallelism. The same thing happens with child sex of 1. And you can see that zero risk tends to create the highest scores, but there's parallelism across those other levels of family risk. This is the interaction, the test of interaction for gender for each level of family risk. So while it looks like these things are crossing here, the fact that we found no significant interaction effect across time suggests that the apparent overlap here can be a function of the within group variance that we're finding existing at these points. Again, pretty clear evidence of parallelism at that level of family risk. I want to make sure that you understand that this is only based on 40 subjects. So when we only have 40 subjects, the issue of within group variance and the estimates of population variance within these groups is going to be much greater. So the difference, the fact that these overlap is a function of our small sample size. Here we have parallelism. We have more subjects at family risk 1. We go on to family risk 2. Again, no overlap. Family risk 3. Oops. Family risk 3, no overlap. Family risk 4. Things are converging a little bit more at the end, but again, this has a fairly small sample size. So I hope that this discussion of running a factorial repeated measures ANOVA has been valuable. I will be posting other videos. Thank you.